Welcome to the video lecture on signals and systems. We are discussing about Fourier transform for a while. In this video, we will discuss a few basic signals Fourier transform. So this will serve as a good example on how to perform Fourier transform on any particular signal. Next, the Fourier transform of a signal function. We know that a signal function can be defined as 1 for t greater than 0 and minus 1 for t less than 0. For simplification purpose, for obtaining the Fourier transform, to bring it into the limit part, we will define Fourier transform in this way. The signal function in this way. The signal function can be expressed as a sum of two one-sided exponential, taking the limit as a tends to 0. So we will define your new signal function now as limit a tends to 0, e power minus at u of t minus e power at u of minus t. So let us substitute this value for the signal function. So let us go with the Fourier transform expression. So Fourier transform integral minus infinity to plus infinity x of t e power minus j omega t dt. Let us substitute your x of t, which is nothing but your signal function. So when you multiply inside, you will get it as limit a tends to 0, integral 0 to infinity, e power minus at, e power minus j omega dt, minus integral minus infinity to 0, e power at, e power minus j omega t dt. Now, you have two e power terms, so simply combine them. You will get it as integral 0 to infinity, e power minus of a plus j omega t dt, minus integral minus infinity to 0, e power a minus j omega t dt. Next, what to do? We will have to take integration. So when you take integration, e power theta will be e power theta divided by the variable value. So on integration, you get limit a tends to 0. This first term will become e power minus of a plus j omega t by minus of a plus j omega. The limits to be applied are 0 and infinity, minus the second term integration, e power a minus j omega t by a minus j omega t. The limits to be applied are minus infinity and 0. Remember, e power 0 is always 1, e power minus infinity is always 0. So next we will substitute the limit values. So where will you substitute the limit values? Wherever you have t, you have to substitute the limit values. Upper limit minus the lower limit. So there you go. We will substitute the limit values. First we have e power infinity and you have e power minus of t. So e power minus infinity. I will tell you the numerator values. So this becomes e power minus infinity by minus of a plus j omega. Now substitute the lower limit 0. It becomes minus e power 0 by minus of a plus j omega. Now coming to the second term. Upper limit minus the lower limit. Upper limit is 0. Lower limit is minus infinity. So when you substitute, you will get minus e power 0 by a minus j omega plus e power minus infinity by a minus j omega. Now look at all these. We will see which becomes 0. E power minus infinity. So the value is 0. So this term becomes 0. E power 0. So the numerator value will be 1. E power 0. So again the numerator value will be 1. E power minus infinity. What happens? This becomes 0. So only the second and the third term will remain. First and the last term will become 0. If you look at the second term, you have a minus here and you have a minus here. So minus and minus will become plus. So going back, 1 by a plus j omega minus 1 by a minus j omega. A tends to 0. So by definition of signal function. So when you put it as a tends to 0, what do you get? 1 by j omega is 1 by j omega. So the value will be 2 by j omega. So Fourier transform of a signal function is 2 by j omega. Next, to apply magnitude spectrum, what is the definition? Square root of real part squared plus imaginary part squared. Real part is completely 0 here. You have only the imaginary part. So what will be your magnitude spectrum? Very simple. Imaginary part squared. So when you put it as imaginary part squared, you have it as j in the denominator. So that will become j squared, which will become 1. Because we make it as magnitude, this will be 2 by omega. And that's how your magnitude spectrum will look like when you substitute various values of omega, get different values of magnitude values and plot it on a graph. And this is how your signal function basically looks like. Last, we have the Fourier transform of a unit step signal. So a unit step signal is defined as u of t will have a value of 1 for t greater than or equal to 0. It will have a value 0 for t less than 0. And in general, we can write your signal function as 2u of t minus 1. So from this, what is u of t? U of t will be 1 by 2 into 1 plus signum of t. So we will use this particular expression. So in place of x of t, we have u of t. So for u of t, we will use the expression 1 by 2, 1 plus signum of t. So this is what we use for taking the Fourier transform. So let us apply Fourier transform for this particular function. So when you apply Fourier transform for this particular function, Fourier transform of 1 by 2 plus Fourier transform of 1 by 2 signum of t. So what is Fourier transform of 1 by 2? So you can generally say that 1 by 2 into Fourier transform of 1. That is, Fourier transform of a constant function is 2 pi del of omega. And Fourier transform of signum function, we already know that it is 2 by j omega. So your next step becomes 1 by 2, 2 pi del of omega plus 1 by 2, 2 by j omega. When you solve this, 2 and 2 will get cancelled. So your first term will be pi del of omega. Again 2 and 2 will get cancelled. So your second term will be plus 1 by j omega. So the Fourier transform of a unit step signal is nothing but pi del of omega plus 1 by j omega. So that's your unit step signal, and this is the magnitude spectrum of the unit step signal. So that's all for today's session. Thank you.